Hi, welcome to another video based on the Sedra Smith book, and this will be the analysis of a Cascode amplifier. Okay, so before I discuss a Cascode amplifier, let's go back a little bit backwards and let's discuss, or let's see, this little circuit. Okay, here's a N channel MOSFET, and here's the P channel, and you have your input voltage. Okay, so if you were to be asked how to derive the gain of the amplifier, well, that would be A sub E is equal to GM, and let's name this MOSFET 1, MOSFET 2, and it would be the combination of the parallel resistance of R1. In other words, there's a resistance from drain to source and parallel with the output resistance from the P channel. Okay, so let's just see how that is derived. Okay, and by symmetry, if we do the analysis for the N channel, then should be the P channel should be the same. Okay, so to see or to derive what the impedance look into the drain, we can draw a small signal model. Like so. And this is the output impedance, R1. And this would be GM, VGS. And we put a voltage source or a test source. And that will develop in IT. Okay, and since we're doing a small signal analysis, the input is shorted. Okay, so I like to define VGS as VG minus VS. Okay, so here we see that this is G, it's connected to ground, so VG is 0, and then we can see the VS is 0, so therefore VGS is 0. Okay, so now we see that we have three currents. Now we define the KCL at the drain, and we have three currents. We have the IT current, which is the negative current since it's going into the node, and then we're going to have a current going through R1, and of course we have GM VGS. Okay, so we have three, so that's a plus current, so we end up with negative IT. Okay, and then we define this current. That current would be VT divided by R sub 1, and it's a plus. And then we have GM VGS. All of that is equal to 0. Now since VGS is 0, that means that this term is 0. So we should have VT equals, and should be I'm not going to skip any step. I'm going to go ahead and just be rigorous. Okay, so then you should have VT IT equals R sub 1. Okay, So that is the impedance looking into the drain of the N channel. Okay, and by inspection you can say the same with the P. Okay, and since you have RO looking up and RO, let's see, RO2 looking up, then there's the parallel combination. Okay, so you have a certain amount of gain. You can call it intrinsic gain. In other words, this is the most gain that you can get out of this topology. But what if the gain is not good enough? Let's say this signal is in a microvolts, very small signal, and you need a lot more gain. Okay, well, that's where a cascode would come in. Okay, so let's see why a cascode is popular. Okay, now typically you'll have a cascode that looks like this. You'll have a P. These are the P channels. And you'll have the N channels. And you'll have your ground. And you'll have your signal. VN here. And these will be V bias. And we'll say V bias 1, V bias 2, V bias 3. Okay, and the output would be here. Okay, so the analysis is going to be the same. Okay, so we know that the gain is going to start with a GM, and typically it's the GM of this one. Okay, and then it's the impedance, at the output node, and this is the output node. So you want the impedance looking in there of the N channel. So this, you can say that is the impedance of the N channels. Okay, in parallel with the impedance of the P channel. Okay, so how do you derive the impedance? Okay, so basically that's what we need to do. Okay, now we can do a little substitution. We know that if you look at the drain of a single MOSFET, it's RO1. Okay, so we can make a little simplification. Okay, we can say we can substitute that for there. So we want to know the impedance looking in there. Okay, so this is V bias, and V bias is basically a DC voltage. Okay, so it's a DC voltage. It's got no signal, no AC signal. Okay, so with this little simplification, we should be able to derive what the output impedance is. Okay, so the bias is shorted, and you'll have a VGS. You'll have a RO1. This is the output resistance of the first MOSFET. You're going to have your GM, VGS, and then this is the output impedance, RO2, and then we can connect our test voltage, which is IT, so forth. Okay, so this is a signal, small signal model, and maybe add a little bit more room. Okay, so we know this is shorted, and this is gate, source, and drain. Let's do a better G there. I'll put a G. Okay, so we got that. So again, I like to define my VGS. VGS equals VG minus VS. Okay, and we look here, VG is equal to 0, and in VS, okay, now here's a little, to make it a little bit more intuitive, let's short this across like this. Okay, and now please note you have current coming out of this test voltage. Okay, it's coming out, so that means that it's IT is coming in from that direction, and if it's coming in that direction, where is it coming from? Well, it's coming from here. Okay, so IT appears across the output impedance of the first transistor, or R-out1. Okay, now this IT then is split between this current source and this voltage source. So the sum of these two equals IT. They enter, IT enters the node, they split up, and then they recombine and they become IT again. Okay, so that helps in that now we can define VS. VS is IT times RO1. Okay, so now we can formally say that VG minus VS, that goes to 0, so we can say that it's negative IT R1. Okay, so now let's do a KCL at the drain. Okay, and let me go back in different color. So we have one current here, so that's IT, and since it's entering, assign it a negative. And then you have this current which is leaving, so that's a positive current since it's leaving the node. And you have this current, the current that is going through RO2. Okay, now to express this current, you have to take the differential. So you can say the voltage across VD minus the voltage across the source divided by R2 naught. So we'll write it down here on the side. So you can say, and let's call this IX for right now. Current IX. So we'll say that IX is equal to VD, okay, minus VS divided by R2 or not 2. Okay, so let's see. Okay, so let's go back here. So you got a negative IT plus GM VGS, and now we're going to say that this is VD VS or 2. Okay, do I have that? I think all of that is correct, and then we say that that is 0. Okay, so now we have to substitute. I'll make another substitution. Let's see, where is my cursor? Okay, we have to substitute this into there. Okay, so negative IT plus, since there's a negative, okay, so it's going to be in a negative. Okay, excuse me. Okay, so it's a negative as GM IT RO not. Okay, so now let's make another substitution. If you notice, VD is connected to VT, so this becomes VT. So we can say this VT. So we can say that, let me see, that it's VT. And there's another substitution. Okay, so that would be negative IT RO1. And I won't skip a step. I'll just be thorough. Okay, so I've done the substitutions. Okay, and I'll distribute this here. Negative IT and let's see, so it should be VT RO2, and hopefully I got this correct. Yes. Oh, if you notice, there's a negative for VS. Is that right? No, it's right here. Yeah, that's right. And it should be a negative IT R sub 2 and R 1 equals 0. So this, we want this on the left side, and then bring everything on the right side. It'll be on the right side, right side. So we'll say VT 2 is equal to, and we got an IT here. So far it looks good. Okay, and then we have this one here. 1, 2, IT. Okay, so now what we can do, factor the IT GM row 1 2. Okay, so far so good. Okay, so now I can get rid of bring all of that distribute that. Okay, so I should end up with, let me see, VT, and I will skip a step, and we'll say that it's RO2 plus GM RO1 times RO2 plus RO1. Okay, so this is the output impedance Z, and let me rearrange it a little bit. I'll say that it's the output impedance of the first MOSFET. It's the first MOSFET okay, plus the output impedance of the second MOSFET, okay, plus the product of both, okay, the product of both R1, R01 and R02, that's the product, multiplied times GM. Okay, so that's pretty good. Okay, so what's the significant about this? Okay, well, let's go back to the original, the first, right here on a simple common source with a active load. We have the output impedance of let's say R1 naught in parallel with R naught 2. Let's assume that these are 1K. Okay, so that means you have an output impedance of about 500 ohms. Okay, and let's say that GM is half. Okay, so that would be 250 volts per volt. Okay, so by using this configuration, using the Cascode, okay, now we notice that we have an amplification of the output impedance. Okay, so let's plug in the numbers. Let's say this is 1K, this is 1K, so that's 2K right there, and then 1K times 1K, that's 1 million, okay, to the 6, and we multiply times 0.5, so this should be 500K. Okay, and then we add the 2Ks, so we should have 502K. Okay, so now we can say that the output gain is GM. Oh, and this is for one. This is for the N channel. Okay, so this is also true for the P channel. Okay, so let's just see if we only treat the N channel. Okay, so we can say that the total output impedance, meaning all of this, assuming that R sub naught or R sub O is 1K, we can say that it's 502K. Okay, and again, if GM is 0.5, then you have approximately a gain of 251 K volts per volts. So there's a huge gain. Okay, so that's when you only take into consideration that you have the N channel. Okay, so the real gain would be A sub V equals GM, and let me go ahead and write the mathematically. We're going to say that it's the R summation of the N channel, Okay, in parallel with the RP channel. Okay, so let me write it out fully. So we can say that it's R sub 1, R sub 2, and so forth, GM in parallel. And let me go ahead and say that this is 1, 2, and say this is 3, and this is 4. Okay. Okay. So then we can say that this is R sub 3, sub 4, plus R sub 3, R sub 4, GM. Okay, so that would be the exact. Okay, now you can do a little hand waving, and since these are so small, these can be dropped. Okay, you can also write an equation or an approximation and say it's GM R sub 1, R sub 2, GM, R sub 3, R sub 4, and GM. Okay, so this is an approximate. Well, this is the exact. Okay, so that is one of the main reasons that cascodes are used. You can get a huge gain because of the output impedance is so huge. Alrighty, well, hopefully that will help. If you have any questions, email me or post your questions on my YouTube channel. Thank you for watching.